Hello everyone, this is Mike Dowding with the SD Mines Physics Department, and we are going to begin our discussions on Chapter 7 today, which is Kinetic Energy and Work. And because we're starting a new chapter, that means that we're going to have a number of definitions that we need to get through. The first of which is the definition of energy. And typically I'll ask people in the class what they think energy is, if they have a good definition. And I've gotten all kinds of decent attempts at this, but even the book itself doesn't have all that great of a definition of what energy is. And so I'm going to go ahead and put my best attempt at the definition on the screen here. I'm going to say that energy is an intrinsic property of the material with the ability to do work. Now this doesn't really help because when it comes to energy, we say, well, it's a property of the material. Well, what kind of property? And we say it's intrinsic. Well, what does that mean? Well, intrinsic typically refers to something that's internal. So, for example, towards the end of the semester, students are going to be expecting a reward of, or for lack of a better word, for all of the effort that they've put into the class. And that reward typically comes in the form of a grade. And so I will issue a grade based on the student's performance, but that reward is external. And so that would be considered an extrinsic reward, as opposed to an intrinsic reward, which is a reward that comes from within. And so that case would be like feeling good about yourself for having gone through all of this physics and performed well and gotten a good grade out of it. So intrinsic is internal, and because of that, it's not always the easiest thing to try and define. There are other intrinsic characteristics that we have, like emotions, and they're not easy to define either. Yet when it comes to energy, if we can measure the energy, then we don't really need all that good of a definition. And measuring the energy means that we're going to need some units, and we will get to those units here in a little bit. But if you're reading along in the book, the first energy that is introduced to us is kinetic energy. And our author just says, here it is, here's kinetic energy, take it for what it's worth, go play around with it, see what you can do with it. They don't really describe where this equation comes from, they just kind of throw it out there and they say, here's the kinetic energy. So what we're going to do is actually take some time to show where that equation comes from. For starters, we are going to be describing energy using capital K. Over here on the right hand side, we have 1/2 the mass times the velocity squared. So the first thing that we can do with this is we can start putting together the units of energy. We have mass in kilograms. We have velocity, which is meters per second, but then that velocity has been squared, so we need to square the units. And all of this looks very, very close to being a Newton. which is a kilogram meter per second squared. But over here we have an extra meter up in the numerator. Well, that's okay. We can take all of that, call it a Newton, and then just sneak in the extra meter, and we're right back to what we had before. So energy can be measured as a Newton meter, but we're going to condense that even further into what we call a joule. So 1 joule is equal to 1 Newton meter, and a joule is going to be the unit for kinetic energy. In fact, a joule is going to be the unit for any kind of energy that we deal with. Turns out kinetic energy is just one type of energy, and it is the energy associated with motion. So when we have an object or a mass which is moving at a certain velocity, then we get a kinetic energy associated with that moving body. Well, let's see if we can figure out where the author got that equation from, because now we know what the units are going to be, but where did that equation come from? Well, before we get to that, let's take a moment and explore the units that we were able to get out of that equation. Because even though a joule is equal to a Newton meter, we can take that combination of units and we can say, well, I know what newtons measure. Newtons measure force. And I know what meters measure. Meters measure displacement. And it turns out that this is going to be one of the simpler expressions for work. And back up towards the top here, that was actually a part of our definition for energy. We said that energy was this property with the ability to do work. So what does it mean to do work? Well, now we can see that if we apply a force over a certain displacement, then work will be done. But what is work? Well, it turns out that work is also going to be measured in joules. So does that mean that energy and work are the same thing, since they're measured with the same unit? And the answer is kind of, because our definition of work is going to be a change in energy. Up here we had kinetic energy, and I said that kinetic energy was one type of energy. As we're going to find out in future videos, there are other types of energy, and energy can be transferred or transformed. So transforming energy means we are going to take the energy and turn it into a different type of energy. But the energy is still measured in joules. If we transfer the energy, that means that the energy moves to a different object or a different mass. But in either case, this means that energy is changing. Whether we transfer it or transform it, that means that the energy is changing, and any time that there is a change in energy, that means that there is work being done. So we've got two equations in front of us so far, We have 1/2 mv squared, and we have Fd equals work. And let's see what we can do with this. We have, so far, an expression that deals with velocity. We have an expression that deals with displacement. If we take force and break that down into mass times acceleration, well, we now have acceleration. And if we can do work to change energy, then that would imply that it's possible to change kinetic energy. Well, so how would we do that? Well, we would have to change something in the expression. We could either change the mass of the object, or we could change the velocity of the object. And for our discussion, I would rather change the velocity of the object, because that's exactly what's going to happen if I start applying a force to a mass. That mass will start accelerating, and that acceleration will cause the velocity to start changing. So what I've written down here is a kinetic energy expression using some initial velocity term, and so we would call this our initial kinetic energy. But then as our velocity changes, we can get some final velocity value at a later time, which would give us a final kinetic energy. So it is possible for our kinetic energy to change. And if we look at the difference in those two values, well, that right there is the definition of work. But we still don't know where this equation came from yet. So let's see if we can put to rest all of our questions here. And remember, I said that so far in all of our expressions, we've had velocity show up, we've had acceleration show up, we've had displacement show up. So in all these cases here. And all four of these are kinematic expressions. So maybe I can put together some kind of a kinematic expression just as a starting point in our attempt to derive this kinetic energy expression. And you'll notice that there is one kinematic variable that is missing from our little collection here, and that is time. And I'm going to continue working without the time. I want to go back to chapter 2 or chapter 4 and just grab the kinematic equation that leaves out time. And if we do that, this is the equation that we need. V final squared equals V initial squared plus 2a delta x. Sorry, we want to keep this one-dimensional for right now. So this is our kinematic equation that leaves out time. Now the biggest transition that we made going from chapter 4 to chapter 5 was the introduction of mass, because once we combined mass with acceleration, then we had force. None of our kinematic equations involved mass. They only involved some combination of those 5 variables. And the same is true here. So I want to update this kinematic equation. I want to update it so that it does include mass. And we can do that quite easily just by applying a mass term to everything in the expression. And I know you're going to be tempted to cancel out those masses, but leave them alone for right now, because we want the mass in that expression. The next thing I'm going to do is I'm going to divide through the entire expression by 2. And when I do that, something kind of interesting happens. Right here, I have 1/2 the mass times the final velocity squared. Right here, I have 1/2 the mass times the initial velocity squared, plus ma delta x. And again, you're still probably tempted to cancel out those masses, but like I said, leave them alone. Because what we have here is the expression for final kinetic energy. And right here what we have is the expression for the initial kinetic energy. So what's all this stuff left over? Well, just start putting it back together. ma equals F, and delta x is the displacement that we've traveled over, and, well, that's just work. So what the expression in front of us is saying is that if we get our kinetic energy terms on one side, that's a difference in kinetic energy. And what is that equal to? Well, it's equal to the stuff that's left on the right, which is work. And that's a definition that we already had. We said that work was a change in energy. Right up here. And by using the kinematics equation from a previous chapter, we've not only been able to confirm that, but we also were able to confirm the equation for kinetic energy that the author threw at us right at the beginning of the chapter. And this is called the work energy theorem. Where the change in kinetic energy is a result of the work that's done in the system. And I'm going to put a little subscript here of net. So work net. Well, what does that mean? Well, think back to force net. What did force net mean? Well, that meant we take all the forces in the system and we add them up. And that's exactly what we're going to do for work. It is possible that we could have more than one force in our system doing work. And what we need to know is what is the total amount of work that's being done in the system, and that will result in the change in kinetic energy. So let's take a moment and talk about work. We said work is the change in energy. Change in energy is delta K, at least at this point in time, until we start to explore other types of energy. But let's go back to that expression that said FD equals work. So here F was our force, D was our displacement. And so all I have to do is apply a force to some object, continue applying that force over a displacement, and that tells me how much work is done. Well, that sounds pretty simple. So let's take a mass of m. We'll put it on a flat horizontal surface, and we will apply a force to that mass pointing to the right, and we'll go ahead and make this our positive x direction. And as that force is acting on the mass begins to displace a certain distance or displacement of d. And what we can do is we can even put some values in here. We can say the force is 20 newtons and the displacement is 5 meters. And my question is, how much work is done? We apply this force to the mass over a displacement of 5 meters, so how much work is done? And you'll notice that I did not even give you the mass of the object. Well, if this is all it takes, if all I have to do is multiply the force times the displacement, then the work done should be 20 times 5, which is 100. And as we said, work is going to use the same units as energy, so that's joules. We have 100 joules worth of work being done on this mass. Well, what good is it to know how much work was done? If I know how much work is done, then I know how much the kinetic energy of our object will change. So far, we know that 100 joules of work have been done, and that's going to be responsible for changing the kinetic energy of our object. So let's go back up to our mass here, and we didn't know what that mass was, but now I'll go ahead and provide a value. We'll say that this is 2 kilograms. And let's also consider that our mass started from rest. So right here at the initial starting point, our mass was not moving. So our next question is, how fast are we moving when we get to the end of that 5-meter displacement? And the work energy theorem, the work energy theorem will tell us that. The amount of work done was 100 joules. I'm going to write out the final and initial kinetic energies in their full form. But keep in mind that the initial velocity was 0, and so that means that the initial kinetic energy was 0. Because the difference in the energies is 100, I guess that means that our final kinetic energy has to be 100 joules. If that's the case, I can now solve for the final velocity of our mass when it gets to the end of that 5 meter displacement. Now I've got a 1/2 out front, and I chose 2 kilograms to be the mass, so those two are just going to cancel out. And I have v final squared equals 100, or my final velocity equals 10. Well, don't forget, anytime you take a square root, there is a consequence, and that is a plus or minus. So technically, the correct answer to this should be plus or minus 10. And these are velocities, so I need meters per second. Well, why does it come out as plus or minus 10? The reason for that is because when we talk about energy, what is energy? Is it a vector or a scalar? And if you're in my class, I always pose the secondary question. When you're trying to figure out if something's a vector or a scalar, just ask where it points. So you have some energy, where does it point? Physically, where does it point? And if that's not making any sense to you, good, because energy is a scalar. Energy does not physically point anywhere. And because work is a change in energy, that means that work is also a scalar. Consider what we've done down here. We've taken information that was a scalar and we're trying to turn it back into a vector. And vectors require directions. Well, the math doesn't know which direction we're supposed to be traveling. All it knows is that we need to be moving with a speed of 10 meters per second, but that plus or minus, that's not going to come into consideration until we actually look back at our picture. So up here, I know that this is the positive direction because that's how I labeled it. And I know that our mass is going to be moving in that direction. So I'm fairly certain that this final velocity will carry that positive label. So really what we're getting out of this is not so much the velocity as it is the speed. And speed, well, that's just the magnitude of the velocity vector. Alright, well, that seems pretty straightforward. Except that this equation up here, that's a bit too simplified. This is not going to work for every given situation. And case in point, I'm going to take that same mass. I'm going to apply the same magnitude of force. And I'll consider the same displacement. So we'll look at this mass as it displaces 5 meters to the right. But this time I'm going to apply the force this way. Instead of applying that 20 newtons to the right, I'm going to apply that 20 newtons up. So we'll let that be the positive y direction. And just take a moment and ask yourself, how much is that upward force going to contribute to getting our mass to move to the right? And the answer should be none. There's a reason that we have x, y, and z axes, and that's so that we can keep everything separate. Things that happen in the x-axis should be independent of things that happen in the y-axis, and vice versa. So in this case, that force will not contribute to any work done. But if I plug those numbers into the expression that we had up before, well, I would still get 100. I would still have 20 times 5 equals 100. But in this case, the amount of work done should be 0. So how do we take that into account? And how do we fix this equation so that it will give us 0 joules of work here, but 100 joules of work up here? And the way we're going to do that has to do with the orientation of those vectors. In the first case scenario, our force vector and our displacement vector were running parallel to each other. In the second situation, they were set up perpendicular to each other. And the equation that we were using, remember that work was a scalar, but what about force and displacement? I thought force and displacement were vectors. And so now we're posed with the question, well, how do you take the product of two vectors and turn it into a scalar? And this is something that I actually skipped over in Chapter 3 with my students. But for those of you that covered this in Chapter 3, this will be a quick review for you. Whenever you have a multiplication of vectors, so let's say we have vector A and vector B. There are two ways that you can multiply vectors. One way is known as the scalar dot product. The other is called the vector cross product. And you've probably heard of dot products and cross products before, and usually they're just referred to that, but it's important to have the full name here because the word out front tells you what the product is going to produce. So a dot product is going to produce a scalar quantity, whereas a cross product is going to produce a vector quantity. And the way we distinguish between the two notations, for a dot product, we put a little dot in between our two vectors. And for the cross product, we put a little cross just kind of on its side here, or an X. And this tells not only us, but people who are looking at our work, what kind of vector multiplication we're doing. So in our case, we need to turn our vectors into a scalar. That means we're going to be using the scalar dot product. And if you've done dot products and cross products before, the first way that we're taught how to evaluate these is that we take the magnitude of each vector times the cosine of the angle that exists between them. So if I had vector A that was 5 meters long at 30 degrees with respect to the x-axis, and vector B was 6 meters long at 90 degrees with respect to the x-axis. So you could very quickly draw these if you wanted to. Vector A would be something right about here. Vector B would be right along the y-axis, since it's 90 degrees from the x-axis. And then theta would be the angle measured between them. So the angle between these two would be 60 degrees. And now we can evaluate what the result of this cross product would be. So we have magnitude of 5, magnitude 6, cosine of 60. Cosine of 60, that's a half. We've got 5 times 6, which is 30, so 30. Oh, not degrees. Well, where'd that cosine come from? Well, we can see here that the angle between two parallel vectors is 0 degrees. I'm going to call this theta 1. Over here, the angle between the two vectors is 90 degrees because they were perpendicular to each other. So what would happen if we applied the dot product to this force displacement multiplication? And we'll do that for the first case scenario here. We can evaluate our dot product by taking the magnitude of each vector times the cosine of the angle between them. Our magnitude of force was 20. Our magnitude of displacement was 5. Cosine of the angle between them, well, cosine of 0 is 1. And so that gives us 100. Just like we got up here. So let's try applying that dot product to the second case. Again, we can evaluate using magnitude and angle. We have magnitude 20, magnitude 5, but now we have a cosine of 90 degrees, and cosine of 90 is 0, which is exactly what we wanted for this situation, because this force is not going to help us in moving in that direction. Now, some of you, even though you've seen the example work out, you still might be a little confused as to where that cosine came from. Why are we using that cosine? So let's take a third example of trying to move this mass. We can still keep the same magnitude values of our force and our displacement, but let's apply the force at an angle. Let's apply that force at, let's say, 30 degrees above the horizontal. So how much work is this force going to do? Well, because that force is at an angle, that force is going to have components, one of which will be pointing in the direction of the displacement. The other component is pointing perpendicular to the displacement. And as we've already seen, those perpendicular components are not going to contribute any work. Only this horizontal component will actually contribute work. And that horizontal component of force can be written as F, surprise, surprise, cosine theta. It is that component of force in the direction of the displacement that is going to do work. And well, all that takes is a slight rearrangement, and we're right back to the evaluation of the dot product. Now, one thing that we do need to be a little careful of is that this theta value was the theta value that I used to measure the orientation of our force. The angle inside of the dot product evaluation needs to be the angle that exists between those two vectors. Now, as it turns out, the displacement vector just happens to be pointing along the same direction as the horizontal, which is where theta was measured from. So I'm justified in using that same angle right here. And with that said, we can now plug in the magnitude and angle. What did we say this was going to be? Oh, I didn't give a value for this yet. I thought I said 30 degrees, but just in case I didn't, there it is. So cosine of 30. So to our calculators, what is cosine 30? We need cosine of 30 times 20 times 50. And so this is evaluating, whoops, to 86.6 joules worth of work. And so now we have an updated version of our work expression. Turns out we do have to consider the orientation of those two vectors such that when we go to evaluate, that theta value will tell us just how much that force is actually going to contribute to displacement in the direction of our displacement vector. Alright, well, I can throw a whole bunch of dot product examples at you, but we've already seen one dot product example over here with our vector A and vector B. But these two examples down here, the ones that I presented us with, these are 2D vectors. We can see that just from the picture that we had over here that was on a 2D plane. So what would you do if you had a system of 3D vectors? So let's take vector C and vector D, and I'll be nice and I'll give ijk components of these vectors. And let's see, for vector D, we'll do 2i hat minus 6j hat, and we'll do plus 7k hat. Yeah. So those are the two vectors. They're out there in 3D space somewhere. Don't bother trying to draw them because that's going to be a nightmare situation. Instead, let's just take the dot product of the two. And the dot product evaluation says take your magnitudes and multiply by the angle that exists between your vectors. So first question, can you get the magnitudes of these two vectors? And if you're a student in my class, we have the magnitude mantra, square root of the sum of the squares. And so square root of the sum of the squares. The answer is yes, we can get the magnitudes of these vectors. And I'll wait to evaluate those magnitudes, but you can go ahead and do it as you're watching the video. So we can get those magnitudes, no problem. But what about the angle? What is the angle of these two vectors? So take your right arm and point it outward at some random direction, and point your left arm out at some random direction, and then ask yourself, what's the angle between them? And that's not an easy thing to figure out, because 3D spatial orientation is just not an easy thing to visualize, let alone try to draw. And so I don't know what the angle is between these two vectors, but I'm not going to let that stop me from figuring out what this dot product is. Because keep in mind that the result of a dot product is a scalar. And when we were talking about work, oops, need to get off that highlighter function. When we were talking about work, it was only the component of force in the direction of displacement that will do work. And that was the whole point of having that cosine there. But again, it's not an easy thing to visualize what component of vector C is pointing in the direction of vector D or vice versa. But actually, that stuff is right in front of us, and we don't even realize it. Keep in mind that even the components of a vector are themselves vectors. The x component of vector C is a vector. It's 3 meters long, and it's in the x direction. The y component, that's 4 units long in the y direction. Z component, 5 meters long in the z direction. Well, I know the components of all of those vectors, and those components are themselves vectors. So what would happen if we considered the dot product of every conceivable combination of these vector components? So I'm going to write all of these combinations out here. And there should be 9 of them. And because we know what each of these components are, maybe we can go through a piece at a time, figure out what each of these combinations is providing in terms of a dot product, and then we can just add everything up at the end because, well, dot products produce scalars, and there's no reason we can't just add numbers together. So for the first combination, I have cx dot dx, and we can evaluate that using magnitude and angle. Well, the magnitude of cx is 3. The magnitude of dx is 2. So we've got 3 times 2. And then I need the cosine of the angle between two components that lie on the x-axis. And when it comes to components on the x-axis, you only have 2 options. They're either going to be pointing in the same direction or in opposite directions. In this case, they're both positive, so they're both pointing in the same direction, which means that the angle between them is 0. Cosine of 0 is 1, 3 times 2 is 6, and so there we have it. That is the evaluation of the first dot product. On to the second one. Cx dot dy. We can evaluate that by taking the magnitude of each times the cosine of the angle between them. Now we can go back up and look at the magnitudes of those 2 components, but here's the more important part right here. Theta, the angle between our components. I've got one component in the x direction, one component in the y direction. What is that? Well, that's a 90-degree angle. Cosine of 90 is 0, and so it doesn't matter what these 2 component values were because, We're not getting anything from that dot product. And that's a critical outcome, because anytime we get an angle relationship of 90 degrees or negative 90 degrees, we're not going to get anything out of the dot product. And that happens anytime we have dissimilar subscripts. So this third dot product is not going to produce anything. This dot product is not going to produce anything. This one's not going to produce anything. This one, well, that one has two y components, so that should produce something. This one's not going to produce anything, or 0. This one's not going to produce anything, but this one should. So cy dot dy, we can evaluate that using magnitudes and cosine of angle. Cy is 4, dy, now keep in mind we're using the magnitude, so I need 6. So what was that, 4 and 6? And then cosine of the angle between them. Now the first component was positive, the second component was negative, so that means we have an angle relationship of 180. Cosine 180 is -1, so I'm getting a -24 out of that dot product. And finally, we have CZ-DZ. CZ has magnitude 5, DZ has magnitude 7. So 5 and 7. They were both positive, so that's an angle of 0. Cosine 0 is 1, which means we're getting 35. So all of that finally comes down to a combination of 6, -24, and 35. So what is that going to make for us? We've got 6 plus 35, that's 41. And we'll have to subtract 24 from that. So I'm getting 17. Oops. 17 for the final answer. Oops. Sorry. 17. And this was just a generic vector problem. But now we can actually take what has occurred here and put everything together into a generic expression. We can see that only the components that matched one another. Oh, where'd my work go? There it is. It's not highlighting the right spot. There we go. So we can see that only the dot products that involved like components actually produced anything out of this dot product expression. And so what we can do is we can write all that out to say that vector C dotted with vector D equals, let's see, we had Cx dx plus Cy dy plus Cz dz. And that's going to be true regardless of the components of the two vectors that we try to put together. We can just modify this equation for the next problem. So here's the next problem. You have a force of 3, 2, 1 newtons acting on a displacement of 10, 4, that should have been a J here, meters. So how much work is done by that force over that displacement? Well, now that we've seen the dot product in action with a generic example, all we have to do is apply that same method to the components that we have here. So F dot D will be the work, and we're going to get that answer by taking the combination of X, Y, and Z components and just adding them all up. So what do we have here? We have a 3 and a 10, we have a 2 and a 4, we have a 1 and a 5. So 30 plus 8 plus 5. What is that, 43? Ah, so close to 42. 43 is what we're getting. Well, 43 what? We were trying to figure out how much work was done. So this is going to be 43 joules worth of energy. And if this is the only force acting along that displacement, then we can take this expression and apply that to any change in kinetic energy for our object. But I'm actually going to end the video right there because this is a lot of information for an introduction to the chapter. But the things that I want you to focus on for right now is that we have the equation for kinetic energy derived. We have the equation for evaluating work, and there are two ways that we can do that. We can use magnitude and angle relationship, or we can use component relationship. It really all depends on how the vector is presented to you. If it's in magnitude and angle, probably best to use this equation. If the vectors were given to you in component forms, probably best to use that equation. And then all of this kind of culminated into the work energy theorem, which we are going to explore some more in the next video. We're going to see some examples of this with multiple forces acting on a mass as it travels along some displacement. So, see you then.